We're in section 8.5, counting principles, and this is goal number 3. And the third goal is to use permutations to solve counting problems. Well, let's first talk about what a permutation is. One important application of the fundamental counting principle is to determine the number of ways that a certain number of elements can be arranged in order. For example, if 20 of you are participating in a race, how many ways can the 20 of you come in first, second, and third place? So to begin, when discussing a permutation, it is an ordered arrangement of objects. So you have to remember that with permutations, order is very important. And the number of different permutations of n distinct objects is n factorial. And we talked about what factorial means in the previous section. We know that the definition of n factorial is the expansion of n times n minus 1 times n minus 2, so on and so forth, until we're down to 3 times 2 times 1. For example, 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, whose product is 720. So I want you to take a moment and review one more time where the factorial key is on your calculator and find 10 factorial. Find its product or its value. So let's look at that. I know that I already have it here, but let's assume I did not. So to find 10 factorial, you would type in 10. And then the factorial key, if you'll go to Menu, Probability, you'll see number 1 is factorial. And there's your value. So 10 factorial is equal to 3,628,800. So I really would like for you to stop right now and find that on your calculator. Don't just let me do it for you. Okay, so remember, a permutation is an ordered arrangement of objects. Let's look at this example. I'm sure you've all tried a Sudoku number puzzle before. If not, a Sudoku number puzzle is a 9 by 9 puzzle, 9 columns, 9 rows. The object of a 9 by 9 Sudoku number puzzle is to fill the grid so that each row and each column and each 3 by 3 grid contains the digits 1 to 9. So the question is, how many different ways can the first row of a blank 9 by 9 Sudoku grid be filled? Okay, well, again, this has to do with order. So we know that the first row has 9 blanks, and you can put the numbers 1 through 9 in there. So for our first digit, we have 9 choices. For our second digit, we would multiply. We have 8 choices left. Then our third digit, we have 7 choices. We have 6 choices. Then 5 choices. Then 4 choices. Then we have 3 choices. Then we have 2 choices left. And finally, we get down to our last blank and we have 1 choice left. So using the fundamental counting principle, we would take the 9 blanks that we have and fill in the number of choices we have for each blank. And because we cannot repeat a number, then our choices decrease by 1 after that. So we have a total of 362,880 choices for just one row. Well, if you understand that this is a permutation and you're using all of the digits, then you'll find that this is equivalent to 9 factorial, which is 362,880. So that's one application of the fundamental counting principle. Well, what about if we don't need all 9 digits at once? Let's look at example B. permutation of n objects taken r at a time. The number of different permutations of n distinct objects taken r at a time is given by this formula. We're first going to complete this using the formula, and then I'll show you how to find this shortcut key on your calculator. So this says find the number of ways of forming 4-digit codes in which no digit is repeated. Okay, well let's first just use the fundamental counting principle. I want you to see how all of this ties together. So if I'm making a 4-digit code, I have a place for digit 1, digit 2, digit 3, digit 4. Notice this says that no digit is repeated. Well, how many digits do we have? Well, we know that in our number system, we have 10 digits, 0 through 9, before we start to put them together. So if we want to fill in the first blank in our 4-digit code, we have 10 choices. Times, in the second blank, because we cannot repeat, we only have 9 choices. In the third blank, because we cannot repeat, we have 8 choices. And in the fourth blank, because we cannot repeat, we have 7 choices. Now in this case, because we're not using a 10-digit code, we cannot just use 10 factorial, but we can use 10, 9, 8, and 7 choices. So we have 5,040 4-digit codes that we could create. Okay, well, how could we use our formula to find that? Well, let's think of it like this. We have 10 digits, and we will use 4 at a time. So with our permutation, it says the number of different permutations of n distinct objects, that would be our 10 digits, taken r at a time, taken 4 at a time. So we know that n is equal to 10 and r is equal to 4. So our formula for permutations of n objects taken r at a time is 10 factorial divided by 10 minus 4 factorial. So that's 10 factorial divided by 6 factorial. Let's factor the 10 factorial until we can cancel with the 6 factorial. So 10 times 9 times 8 times 7 times 6 factorial. And if you notice, those 6 factorials cancel, and we have exactly what we had when we used the fundamental counting principle. So 10 digits taken 4 at a time gives us 5,040 different combinations. So I do want to encourage you to use your calculator to calculate this. So we already know that n is 10 and r is 4. So let's look at how do we find that key, that shortcut key on our calculator. So to calculate 10 permutations taken 4 at a time, we would go to, from the calculator screen, go to Menu, Probability, and Permutations. And you can see that we have NPR, and you would enter the value for N first, type in a comma, and then the value for R. And that gives us 5,040 combinations. So go ahead and practice that one time and make sure you can find that NPR and calculate it on using your calculator. I would like you to try example 2 on your own and then turn the screencast back on and check your answer. So at the Daytona 500, if there are 43 race cars, then there are 74,046 different ways that the cars can finish in first, second, and third place. So we have 43 elements taken 3 at a time, and order is important when you finish first, second, and third. Therefore, this is a permutation. You could also draw out a blank for first, second, and third place, and you know that there are 43 cars that could finish in first place. There are only 42 cars that could finish in second place, and 41 cars that could finish in third place. And this is equivalent to 43 racers taken 3 at a time. Let's finish up our discussion of permutations with something called distinguishable permutations. And I hope by the end of this discussion you can describe, and you can get rid of that typo, how to know when to use the formula for a permutation and for a distinguishable permutation. Let's look at the scenario about the building contractor, and then we'll discuss how we know when to use that. A building contractor is planning to develop a subdivision that consists of 6 one-story houses, 4 two-story houses, and 2 split-level houses. In how many distinguishable ways can the houses be arranged? So if we lay out a marker for 6 one-story houses, 4 two-story houses, and 2 split-level houses, the question is, how many different ways can we arrange those? For example, we could have all 6 one-story houses beside each other. So here's a 1, 1, 1, 1, 1, 1. And then we could have 4 two-story houses. And then we could have 2 split-level houses. I'll do S for split-level houses. And that's one arrangement. And then we could move this one-story house to the end. And that's a second arrangement. And then we could move the second one-story house to the end, and that's a third arrangement. So we're trying to determine how many different ways we can arrange those. So this is when we would use distinguishable permutations, because we have repeats that we want to put in different orders. So the number of distinguishable permutations of n objects, where n of sub 1 is one type, n sub 2 is another type, and so on. So first of all, let's look at the definition for n. n is the sum of each different type. So we have 6 one-story houses, that's one type, plus 4 two-story houses, that's a second type, plus 2 split-level houses. So we have a total of 12 houses for our value of n. And then remember, this says that n sub 1 is one type of house. So we have 6 one-story houses. There's our n sub 1. We have 4 two-story houses. There's our n sub 2. And 2 split-level houses. There's our n sub 3. So for the distinguishable permutations, we have 12 factorial divided by 6 factorial times 4 factorial times 2 factorial. And if you take a moment to calculate that, I know that I can factor 12 factorial all the way down to 6. So 12 times 11 times 10, 9, 8, 7, 6 factorial divided by 6 factorial, and then 4, 3, 2, and then 2 factorial is 2. So these 6 factorials we can cancel. I know that 4 times 3 is 12, so I can cancel this 12. 2 times 2 is 4, and that will divide into 8 2 times. So that gives us a total of 13,860 ways that we can arrange these houses. Now, you don't have to expand and cancel, but the reason I expanded and canceled is because I wanted you to see that the formula for distinguishable permutations is different than in PR, or in objects taken 4 at a time, or taken R at a time. So this is showing us all the number of different arrangements that we could come up with, given 6 one-story houses, 4 two-stories, and 2 split-level houses. If I ask you the number of choices, if you were choosing between houses, remember that would just be 6 times 4 times 2. But in this case, you've got to think of all the different ways we could arrange.